In this example, we're trying to find the first four natural frequencies of a tapered bar undergoing axial deformation. Unlike the first example, in this one where we have a taper in the bar, we're going to have a non-constant cross-sectional area, meaning that we don't know how to find the analytic solution from the techniques we developed in the previous section. So we don't already know analytically what the answers should be. So we don't have a way of confirming the numbers that we get here, but we are going to be able to get an approximation or something we think is going to be near our solution later on in the problem by treating it as though it had no taper. So we need to find here omega n. We're just going to look at the first four as we're going to see. Now, in this version of the problem, we are going to use a fixed 5-element finite element analysis. And when we revisit this later, we're going to increase the number of elements we use in our analysis. Now, the taper is going to make our analysis a little bit trickier than we saw in the previous problem because of that non-constant cross-sectional area. So what we're going for is starting with this large diameter of 0.1 meters, and then we have this linearly decreasing diameter until we're at 0.02. And it's going to be fixed here, and that is going to influence our boundary conditions when we apply the FEA, and also when we take our analytic approximation of what the problem is. So we need to take this and turn it into a 5-element finite element analysis. Now our rule with our finite elements is that every one of the elements we create itself has a constant material, so the E and the rho are going to be constant, and a constant cross-sectional area. So with only 5 elements, we're going to see how we are going to be kind of approximating what the figure looks like. But when we revisit this and use more elements, we're going to capture more realistically how this taper is operating. So for this first element, it has to look like a rectangle, so it has to have that constant cross-sectional area. We'll decide what that area is in a moment. And then what we can do is we have another element that it's attached to that can have a smaller cross-section, so a smaller diameter. And then we'll have element 3 and 4 and 5. And it's also fixed to the wall there. So we'll have element 1, 2, 3, 4, and 5. And then we're going to have our degrees of freedom, which we will have here U1, 2, 3, 4, 5, and 6. Right, so that is the horizontal motion of each node. And each element is going to have a node on the left and a node on the right. So I'll put those dots here, but the node number is the same as the degree of freedom number 1 through 6. And each of these will have its own area. So we'll have, I'll mark it here, an area 1, because that's going to come into play when we create these local mass matrices. The changing area is going to affect it. And the same thing is true for the local stiffness matrix. If each one has its own area, we're actually going to see that each one of these elements has a different local mass and a local stiffness matrix. In contrast to the previous example, every element had the same area, the same as Young's modulus, the same density. So actually all the local matrices were exactly the same. And in this case, we're again going to use uniform size of our elements. So each one is going to have a length of L over 5. So we can see in this kind of schematic here that it kind of approximates the original shape of the taper, but we have these kind of sharp edges here at the edge of our boxes that are not really realistic to what the tapering looks like, but it generally does have this decreasing area as we go from the left to the right. Now when we look at this and we can add a lot more elements, that tapering, that reduction area is going to become smoother the more elements we add. But for this first version of the example where we're specifically using 5 elements, we're going to see that it does look very boxy, and the results are going to reflect that. So the question is going to be, what should we use as the cross-sectional area for element 1, 2, 3, 4, 5? and the cross-sectional area is going to depend on the diameter of each one, because each element has to have a constant diameter so that it has a constant cross-sectional area across it. Well, going back up to the original problem, there's different ways we could address this. So we could say, all right, I'm going to, each element, like this one that starts at x equals 0, I'm going to make element 1 have the constant diameter of capital D, the 0.1 meters. So whatever node is on the left, I will just use that as the diameter for the entire thing. But then the problem is going to be, if we kind of superimpose the actual taper into this. So if that is the case, what's happening is we're overestimating the amount of material on each of these elements if we are using the left node as the diameter for the entire thing, since the diameter gets smaller left to right. So we're going to be overestimating the amount of material have, so we are going to be coming up with a different estimate than the actual of what the natural frequency is. Alternatively, we could say, well, let's take the right node, whatever the diameter is there, we're going to say is the diameter of the entire element. So it would look more like this. So this red is, again, the actual taper. I'll just put it on top of the screen. So the problem with using the right node as the diameter for the whole thing is now we're underestimating the amount of material that should be in each of these elements. And again, that's going to throw off the natural frequencies that we come up with. So both of these have their issues. And really, once we use a lot of elements, it's really not going to matter, because as the element size or length gets really, really small, that difference between the actual area of that slice and the approximate area of the slice is going to go basically to 0. But when we only use 5 elements, we will see it makes a big deal. So what I'm going to do instead is actually split the difference. I am going to use the average of the left diameter and the right diameter to approximate the diameter of each of these elements. And again, all 3 of these will converge to the same results if we use enough elements, but using the average is probably going to converge a little bit quicker. But no matter what we do with only 5 elements, we're going to see the answer is not very good. So we can look at the code now, and again, I'm going to say that the area of each one is going to use, I'll call it the average diameter, which is going to be the diameter of the node on the left plus the diameter of the node on the right over 2. And this is how, for each of the elements, is going to be pi d bar to the 4th, or d squared over 4, is how we'll calculate the area. Again, for the diameter, I'm using the average. You could use the left or the right, and eventually we'll get the same results. Before we get to assembling our matrices, we have to look at our map list here. Again, going to be pretty straightforward here. I have these 5 elements, and I just want to know which node is on the left and which node is on the right. So the left node, the right node. So element 1 is going to be 1 and 2, 2 and 3, 3 and 4, 4, 5, 5, 6. This process will be automated once we add more elements to it, because we can see what the pattern is pretty readily here of the node number on the left versus the node number on the right. But this is how I'm going to know what column and row to put in the global mass and stiffness matrices to put my local mass and stiffness matrices. Looking in the code, we see that it starts looking pretty similar to the previous problem. I'm going to pre-allocate my global stiffness matrix, my global mass matrix. I'm going to create the map list that I just wrote. I have my left diameter, my right diameter of the tapered bar, the total length I was given, and then the length of each element. Again, I'm using equally sized elements, so I'm just dividing the length by my number of elements, which was 5, which made 6 nodes that I allocate up top. I'm also going to calculate the area of each of the elements. We didn't have to worry about that in the first one because they all had the same area. But here I want to know what area I'm going to use for the 1st through the 5th element. So I'm going to pre-allocate that. This is where here in 23 I am going to determine the diameter that I'm using for each one. Now this is going to give me first the nodal diameters. It's a linearly tapering beam, so I know it's just going to be a linearly interpolation as I go left to right of the left diameter to the right diameter to find the diameter of each node. So I'll just run up to there, and we can find these di. So that's the diameter of each of my 6 nodes. And that's going to come into play when I calculate the area in my loop. Again, I'm given the Young's modulus in the problem and the volumetric density in the problem, so I will include those here. In this example, those are going to be constant. Now we can go in to build our local mass and stiffness matrices and then put them right into the proper spot in the global mass and stiffness matrix. So let me rerun everything up to the for loop just so we can see the sizes of everything we have here. So I pre-allocated that capital K and that capital M. They are 6 by 6 because I have 6 nodes in this problem coming from those 5 elements. So most of this loop looks really the same as what we saw in the previous example. The only difference here is I am calculating the area for each of my elements as I go. So when j is equal to 1, for example, I'm on the first element. So what I'm doing is I'm taking the average diameter of the left node of element 1 and the right node of element 1. So that's why I'm using the jth term and the j plus first. So this di of j is the left diameter at that node in the real problem, and j plus 1 is the diameter on the right. I'm taking their average, squaring it, dividing it by 4, and multiplying it by pi to get the cross-sectional area I want to use for the jth element. So that is going to decrease as I go through. So let's just see what a local matrix looks like. So this is for element number 1. I just want to see what my KE and my ME look like. So again, they're going to be 2 by 2 for these axial problems, and they'll slot it into the right spot here. All right, so that's the KE and the ME. The numbers don't really mean too much to us, but just for comparison, let's look at the second element just to see how they differ. So I run just that for element 2. And ME, so notice here the ME is different as now we should expect as that cross-section changes. The ME is now, let's look at the main diagonal, 7.1, whereas in element 1 it was 10.4. And if I go all the way to the extreme, the last element 5, let's just look what that is. ME should be even smaller. All right, so the main diagonal is now 0.966. I'm in scientific notation, so that mass decreases as I go from the first element to the 5th element. Whereas in the previous problem, the KEs were all identical, the MEs were all identical. So I'm going to run this loop. It's behaving the same way it does before. I make this 2 by 2 local stiffness matrix, local mass matrix, and then I immediately slot it in to the global mass and stiffness matrices using that map list that is identifying what node is on the left and the right, which tells me which column, which row to put it, the local mass and stiffness matrix in for the global mass and stiffness matrix. So I'll run this whole piece here and let that run. Now, if I look at big M, we see here my global mass matrix is 6 by 6, and now about half of it are zeros. And if I look at K, same idea here, about half of it are zeros. I have non-zeros on the main diagonal and then 1 off of the main diagonal as well. So global matrices are now assembled. So now what I need to do is I have to enforce my boundary conditions, then I'll be ready to solve for my natural frequencies. So back to our problem statement. Again, we were told to use 5 elements, so we have these 6 degrees of freedom established here. So this U is going to be U1, U2, keep going, 3, 4, 5 to U6. Those are our 6 degrees of freedom, at least initially in this problem. Now we want to enforce our boundary conditions. For these axial problems, what we're going to do is only enforce deflection equals 0 boundary conditions, not anything about axial strain. However, in this one, our boundary conditions are different than in the first example. We have that U1, as defined here, is 0. At the wall, that node cannot move left or right. And also, though, U6 is 0. That last node is also attached to the wall in this fixed problem. So we have two boundary conditions on displacement or that we have to enforce, which means since it's the first and the sixth node, then in the M and the K matrices, I am going to eliminate for U1 the first row and first column, and the sixth, or in this case, the last column and the last row. And that is going to be the same for K. So it's going to be 6 by 6. I completely remove first column, first row to enforce U1, and now sixth column, sixth row to enforce U6 being 0. In the previous example, we only had one displacement boundary condition, so only, and that was on U1. So first row, first column were eliminated. Here, two are eliminated because there are two deflection boundary conditions set to 0. So looking in the code, apply these boundary conditions, which I'm doing in 46 and 47. So I'm taking my original K, which is 6 by 6, and I'm going to start at the second column and second row, so that will eliminate the first, and I will keep all but the last column and last row. So that's what this end minus 1 is doing. I could have just put K of 2 through 5, 2 through 5, but we're going to see I'll use the same notation when we expand this, so it's a little bit more robust when we add more and more elements to what we're solving. So if I run 46, 47, now we see in the workspace K is now only a 4 by 4, M is only a 4 by 4. It was 6 by 6, took away 2 degrees of freedom that were fixed displacements, and we're down to 4 by 4. Which means, even though we started with 6 degrees of freedom and 6 by 6 matrices, since it's been reduced to 4, we can only find 4 natural frequencies. And we're going to see that they're not that close when we examine this problem further, but we can only even get 4 of them now. So next step, I'm going to take the eigenvalues of M inverse K, take the square roots, so that's my natural frequencies, and as always with these problems, I need to sort them. So running that, these are the 4 natural frequencies I get with the 5-element FEA code. So the lowest natural frequency is about 5385 radians per second, and then the highest one, 25,400 radians per second about. Now, how do I know if these are any good? Right now I don't, and with so few elements, I can almost guarantee that they are not very good. But for comparison's sake, we would like to have an idea of how close we are, if at all, to what the actual answer is. But once again, the problem is in this problem, since the area, cross-sectional area is not constant, we cannot find the analytic solution, at least using the tools we know from the previous section. So what we can do, though, to get maybe an idea, at least are the magnitudes going to be close, is solve a problem that we do know how to do analytically instead. And this is where we get to that choice between, do we want to solve for difficult problems, do we want to solve an approximation of the exact solution, or do we want to solve for the exact solution to an approximation of the problem? Well, so far we did the former. We have an approximate solution to the exact problem. We kept the taper in. Now we chunked it into these fairly big rectangles here, and that's where the approximation is coming in, but we didn't change the nature of the problem itself. It's still tapered. So what we can compare this to get an idea of how close we might be is find the exact solution to an approximation of the problem, the approximation being one that we do know how to solve analytically. So for example, if this taper were not here, if it were a constant large diameter D or small diameter D beam that was fixed, we do know how to solve that. So what we can do is kind of cheat a little bit and say, well, without the taper, we actually do know what this should be. And at least we can get a solution that might be close or at least in the same realm as the solution we get for the true problem. If we go through the steps analytically for this fixed beam of what the natural frequency should be, or we look it up in the table, we know that analytically for a non-tapered beam, that the natural frequencies are going to be n pi c over L. So we're going to be able to find the first 4 because we can use n equals 1, 2, 3, and 4. And we know that C is going to be the square root of E over rho, both of which were given to us in this problem. And we know the length of the beam as well. Now notice in the natural frequency calculation, actually the cross-sectional area does not appear at all. So whether we were to treat this non-tapered beam to have the same large diameter across the entire length or the same small diameter across the entire length, as far as a non-tapered beam goes, the natural frequencies are going to be identical in those two situations. So really we just need to calculate this once, and then we can get some kind of comparison to what we just got with the FEA. Going back into the code, I can do that calculation now from the analytic, assuming no taper. So I can calculate my C value, and now down here, this is where I'm doing my n pi c over L calculation to get the first four natural frequencies from the approximate analytic approach. And now I will put them all down. I'll just run this whole thing now so we can see the natural frequencies we get from FEA versus the approximation from the analytic method. All right, so this is what we get in the end here. So from the FEA, our lowest, our first natural frequency, from only this 5-element FEA, 5380 about, versus analytically without a taper, 5280 versus 5380. And then the second natural frequency, we're high by about 1,000, we're high by about 3,000, we're high about 4,000, at least from the analytic method. So the problem we have at the moment, though, is on the downside, we don't know how close we are to the answer because probably the analytic answer is not correct because we're assuming no taper when we got the analytic solution, but there is a taper. So we can't trust these numbers. These are not necessarily the true values this time, whereas in the previous example, we knew those were, at least theoretically, the correct values. And we also can't trust the values we got from the FEA, though, because we have so few elements that there's probably going to be a lot of precision error in what we got. So at the moment on this problem, we can't say too much about these results, except that, at least as a kind of ballpark estimation, from an analytic method without a taper, all of our orders of magnitude are the same as what we're getting with the FEA. So possibly, and we'll confirm this when we do the follow-up version of this, possibly we have a decent start on what the answers should be from the FEA, but we have the problem of using too few elements right now to really trust what we're getting. And from the analytical method, we can't exactly trust those either because that does not account for the taper that's in the beam.